inverse relations. The actual topic of inverse functions really isn't something that we look at until next year. Right? So we won't actually be tested on this inverse stuff till next year, but it seems like an appropriate thing to look at now, seeing we're talking about functions and relations. So just a quick little bit about it. So if y equals function x is a relation, then the inverse relation is simply found by swapping the x and the y around. So y equals x squared, its inverse relation would be x equals y squared, and so on. Oh, actually, here's my example. X cubed plus x. Just swap the x and the y's around. Okay. Now, that's interesting. But what's more interesting is this. As far as the picture goes, because we swapped the x and the y's around, what effect do you think it has on our picture? So it's actually reflected in the line y equals x. Y equals x. The domain of the relation becomes the range of the new inverse relation, and vice versa. So the range of the relation becomes the domain of the new inverse relation. Okay. And there it is. All right, look, y equals x squared, domain is all real x, and the range is y is greater than or equal to 0. But if we swap the x and y's around, the domain becomes x is greater than or equal to 0, and the range becomes all real y. Amazing. Anyway, they're inverse relations and they're okay, but inverse functions are more important. So if that inverse relation that we've created satisfies the rules for a function, then we call it an inverse function. Okay. So you might remember we tested for functions with a vertical line test. Well, because we swapped the x and the y's around, to see whether it has an inverse function, we can test with a horizontal line test and apply the same way. Or another way of doing it, swap the x and the y's around, but then make y the subject. If you end up with something that's unique, then it's an inverse function. So there's y equals x squared, x squared. Visually, horizontal line test applied to it, it's going to fail. All right? Draw it in there, no good. So, only has an inverse relation, doesn't have an inverse function. Or, so this is what I mean with algebra, just using algebra. Swap the x and the y around. If I make y the subject of this, I get plus or minus root x. It's not unique, because it's plus or minus. So therefore, no good. No good. Right? Not unique. As opposed to a very dodgy cubic. That one satisfies the horizontal line test. So visually, yeah, that's going to have an inverse function. If I swap the x and y's around, x equals y cubed, well, y equals the cube root of x, it's unique. Because when we're dealing with real numbers, there is only one cube root of x. Now, another way of looking at it. If the inverse relation of y equals function x is a function, then y equals function x has an inverse function. But what should happen is this. If I substitute the function into the inverse function, they should cancel each other out and I'll be left with x. And vice versa. If I substitute the inverse function into the function, they should cancel each other out and I get x. So, this is a function. It's actually a hyperbola. It's been shifted a bit, but it is a hyperbola. The inverse function will be x equals y minus 2 on y plus 2. If I make y the subject, there it is, 2x plus 2 on 1 minus x. So if I substitute the function into the inverse function, a little bit of algebra to do, but eventually, yes indeed, we get down to x. And the reverse should also work. If I substitute the inverse function into the function, again, bit of algebra to do, but it comes down to be x. Right? Because inverses should always cancel each other out. Right? It's the same as addition and subtraction. Cancel each other out. Multiplication, division. Cancel each other out. And then to draw it, just to finish off here, let's draw it. So we said it was a reflection in y equals x. So any point on the line y equals x will stay there, but everything else translate at 90 degrees like a mirror. So let's look at it. Whoop, there it is. And in fact, if you get your head, turn it 45 degrees, oh yeah, look at that, it's symmetric. Okay? But I guess the key points to plot are like the x-intercept of the original one becomes the y-intercept of the new one, and vice versa. So they're key points. Probably those turning points would be key ones to plot across as well. Things like that. All right. That's, all jokes aside, a little bit of an introduction there on inverses.